Good morning, everybody. So, welcome back to today's morning session of the school come workshop on data analysis in cosmology and astroparticle physics. In this session, Professor Dhiraj Kumar Hajra will continue on his discussions and tutorials on cosmic microwave background. So, over to you, Dhiraj, and a very warm welcome to all of you once again. Yes.
Thank you, Supradita. Okay, so I have shared the slide with you, CMB hands-on session. So let's have a look at the slide. I will also share the screen. Okay. Before I start this hands-on session, any questions if you have, regarding yesterday's session or the assignments that I have given during the inflation hands-on session? Any questions? If there are any questions, please unmute yourself and let me know. One good thing is that you have experience, right? I mean, when we discussed in the inflation hands-on session, that if you discuss that, okay, I'm not able to do this thing or somebody is able to do this thing. So if there are mutual interactions, things usually stay in equilibrium, right? So you understand something that you may not understand while I'm giving the lecture. So in the hands-on session, it is very important that whatever we have discussed, if you have any questions, queries, or if you have tried running those things, if you have failed, or if you have even succeeded, if you have understood something more than what was written, you can please share it here so that we can all discuss about that. Okay. Okay. If not, then let's move on. Yesterday, I did not discuss this part, getting the angular pause spectrum. I discussed it. Okay. There is an amplitude part. Yeah. Okay. So Arijit, please unmute yourself and can you explain which part would you like to understand more? Yeah, and sometimes when I'm speaking, I'm not looking at the chat box. So if there are any questions, please unmute yourself and ask directly, okay, so that I don't miss any questions. Arijit, you can unmute and ask the question. Am I audible?
Yes, you are audible.
So, is there any problem with? Is everybody having any problem? Okay,
Okay, hello, sir.
Is this Arijit?
Yes, sir.
Yeah, tell me. Yeah.
So you are expressing the equation while there was a curly M part which you said about the amplitude part in the equation earlier yesterday. So what is the amplitude? I mean, is there any dependence of the in the amplitude?
Oh, yes. You see that amplitude is basically the scattering amplitude, right? So in quantum mechanics, whenever you calculate a scattering, let's say Coulomb scattering or Compton scattering, you can calculate the amplitude of the scattering and integrate it over the momentum space. You can, what I define is that the scattering cross section, sigma v, that is the thermally average scattering cross section. Okay. So you see that is important because every scattering is different. I mean, happens at different amplitudes. For example, Coulomb scattering happens at different amplitude, and Compton scattering happens at different amplitude. And we know those things because we have tested them by different experiments on Earth. We know those amplitudes. We know the cross sections. So we can simply put those, and then we can understand what the CMB looks like at the recombination epoch, and then we integrate them to today. Now the question is that okay, now the thing is that let's here is one extra thing I would like to tell you. Let's say dark matter. Okay, we assume that dark matter doesn't scatter. Okay, dark matter doesn't scatter, it only interacts with gravity, and since it interacts with gravity through the gravitational potential, all the other all the other over densities, evolution of other over densities changes over time. So Now you say that I have a high energy theory in which I can calculate the scattering amplitude between dark matter and normal matter. Okay, let's say electrons or protons. Then you can ask the question, can I constrain that? So I can write the equations in the sigma v, in the v dark matter equation or delta dark matter equation. You remember the right hand side was empty because there was no scattering term. But now there will be different terms depending on your sigma v, the thermally average scattering cross section of dark matter and other particles that your theory is giving, okay, or estimating. What you do is that now you evolve this dark matter equation forward, and then when you get the constraints, you will get a constraint on the amplitude depending on the data. Is it fine?
Yes, sir. Thank you, sir.
Okay. So remember, this is the scattering amplitude you're talking about. The now by amplitude one, we are going to discuss the CAMB and Cosmo IMSc part. By amplitude, we'll talk about the amplitude of the scalar perturbations. Okay, amplitude of the primordial power spectrum. Okay. Now, okay, so this is the flowchart of CAMB. I hope that you have already downloaded this. Okay, I had given some instructions of downloading a few things. Okay, and data, likelihood, line grid analysis. Okay, if you are able to join Sci server, please go there. And if you have already copied my directory, you will find a directory called Cosmo MC. Can you change to that directory?
Yes, sir.
Open a console, change to that directory. If it doesn't matter whether you are in your own machine or you are in the Sci server. Only thing is that in your own machine, your G Fortran has to be G Fortran version 6 plus or 7 plus. So change to the Cosmo MC directory, then change to the CAMB directory. And in the CAMB directory, inside the CAMB directory, go to Fortran. Fortran. Okay, let me do one thing. Let me just share a part of my screen so that whenever I change the screen, it doesn't matter portion of the screen. Share. Are you able to see my Sci server account where I have opened the files?
Yes, sir.
Okay, good. Now, I hope that you have reached this. All of you have been able to reach this folder, Cosmo MC CAM Fortran. Okay, again, Cosmo MC CAM Fortran. Anyone who have not been able to change to this directory? Anyone having any problem? Okay, I'm assuming that everybody have been able to change to this directory. Now, let's see the flowchart. Okay, the flowchart is saying that how the angular power spectrum is computed. So initial condition, you remember I had written CL can be computed by a convolution integral between the power spectrum and the transfer function. All right. So the transfer function is obtained with the solution of the Boltzmann equations for all the particles. So for photons, you can get that. The final answer is basically, and then you get the ALMs and then multiplied by that, it gives you the CLs. I mean, sorry, the correlation function or the square of that is giving you the CLs. When you convolve this transfer function and the power spectrum, you get the CLs. Okay, that is coming from the from the formula that ALM correlation gives you the CLs. That is what I discussed in the last, so the second Jamboard. Okay, second Jamboard of the CMB. So what you need is that you need initial condition. Initial condition means that you need an initial power spectrum. And for slow roll, the initial power spectrum, as I said, can be determined by two parameters. One is the amplitude and one is the tilt. As I said, if a power spectrum is completely scale invariant, you can simply describe it by one parameter called the amplitude. That is the scalar power spectrum amplitude. And if you have a tilt, then you can basically express it as with two parameters. One is amplitude and one is the tilt. And the tilt is called scalar spectral index. The amplitude is denoted by AS and the tilt is denoted by NS. And we have already discussed the NS constraints. Okay, now you have to, what you need to give to CAM is one is the background parameters. What do you need? For example, omega baryon H square, omega CDM H square, and then H naught and tau. These are the background parameters, let's say. You may have questions that, okay, can anybody say that, oh, I mean, why I'm not using just omega matter H square? So omega baryon H square and omega cold dark matter H square gives you the omega matter H square, right? So I can just have three parameters. So for example, if you are using supernova data, if you have encountered this, if you have supernova data, you can simply work with omega matter H square and omega k if you assume your universe is not flat, and that's it. Why here we are needing extra parameters, omega baryon and omega, why we need to further divide the omega matter into two parts?
So they affect the power spectrum differently. The omega p affects the odd peaks, and the omega matter, the omega dark matter affects all the peaks. Yeah,
the simple, exactly. The simple thing is that the supernova data is not sensitive to the omega baryon H square or omega dark matter H square. It doesn't matter if it just depends on the matter content of the universe or the dark energy component of the universe. When you go to some other data, that data has some characteristic. For example, CMB has certain characteristic, that the baryon acoustic oscillation. Okay, when there is baryon acoustic oscillation, you need baryon density. That is why you need to further subdivide. Okay, so it was a very simple question, but I needed the answer because if we need to discuss the supernova data, we will also need that. Why we are using the omega baryon square here and not there. So we have background. We can solve the Boltzmann equation using CAM, and we do the convolution. I'm going to show you the codes there. Then you get the unlensed angular power spectrum, right? And I also mentioned yesterday that there is lensing. If you have lensing, then your CLs gets mapped to a different angle. So let's say the photon is coming towards you, but there are some structures in between, and we have structures in between, and photons gets lensed. So the photons or the anisotropies gets mapped onto a different direction. So n goes to n prime. Lensing takes care of that, and you add the lensing part and you get the lensed angular power spectrum. And remember, this lensing appears only at the intermediate or the small scales. Why? Because the structure, it depends on the correlation of the structures. Okay, there are not much correlation of the structures at very large scale. That is just those correlation are basically only coming from the primordial power spectrum. Okay, then from the lens angular power spectrum, you add foreground and you calibrate for different frequency channels, and then you get the angular power spectrum that can be compared with the data for different frequency channels. Okay, now let's come back to this part, and let me open initial power.f90. Please open initial power.f90. Are you there?
Yes, sir.
Okay.
Yes, sir.
If I'm moving fast, please stop me. So you will find T initial scalar power. Just a second. Here. Let me see if I can highlight. Yes. A function called function T initial power law scalar power. Okay. Here you see, I am defining, it is defined here as AS, the amplitude times, if you take this log and everything outside, if you just cancel log with exponential, you'll find that this is K by K naught. See, ln rat, ln RAT is basically log ratio, is ratio between K by the pivot scalar. Pivot scalar, usually, I mean, there are different conventions. Usually people use 0.05 megaparsec inverse. So K by K naught. So you take log K by K naught. So when you take exponential of that, it is just K by K naught to the ns minus 1. For our discussion, it is only that. We only need that. So ns minus 1. There is a tilt. Then after that, there can be a running of the spectrum. For example, if it doesn't have, if the power spectrum doesn't stop at a tilt, if it has certain type of bending, then you can parameterize with another parameter called running of the spectral index. Then there can be running of running as well, where you can assume that your power spectrum is having some wavy features. So the running also changes with the cosmological scales. So this is as far as the power spectrum goes. The very simple function, if it is having a tilt, as K by K naught whole to the ns minus 1. Okay, all right. Let me see. Okay. Now let me open this CMB main.f90. Please open CMB main.f90, where I'm going to show you where the convolution is being done. Just give me a second. Mhm. Just a second. Okay, this is in this new version. It is this is the limber. Okay, let me find that in my version and then make the comparison. In the meantime, we can open the INI file. Go back to CAM and open INI files. Okay. And then open Planck 2018.ini, Planck underscore 2018.ini. So this has the 2018 best fit values for which you are going to calculate the CMB angular power spectrum. Okay, so you see there are these logical flags that you have to set true or false in order to get the power spectrum of your choice. For example, we simply cancel vector CLs. We are not worried about tensors now. Get transfer function, it is true, so you get the matter power spectrum. So let's just rename it as base. Okay, baseline, base or baseline. Here Lmax scalar is given, that how much Lmax you would like to see. So how much small, what small scale you would like to explore. So Lmax for Planck is 2500. Usually you have to put it a little bit extra in order to incorporate the lensing of the order of 100 or 200 extra. So you write it as 2700. This is not needed. Lmax tensor is not needed if you are not interested in the tensors or your tensor to scalar ratio is not large. Okay, now you have this omega baryon H square, you have omega cold dark matter H square, omega neutrino H square, omega K 67. Dark energy model is PPF, so and it uses W0WA. Okay, W0WA with the CPL parameterization. It is set to be W equal to -1. That means we are assuming lambda. We are not using any sound speed of dark energy. We are not using that. So it is, sorry, I mean, we are not using any sound speed that is different from 1. And temperature CMB is given here, helium fraction, neutrino degeneracy, etc. So we are not going to discuss that. Here, you see, here the scalar amplitude is given. That is the AS, 2.1 into 10 power minus 9. You remember when I have plotted in that inflation notebook, in the bingo notebook, I had plotted, okay, I had plotted in the GNU plot. So you remember, if you remember correctly, that I have redefined a function 2.1 into 10 power minus 9 times k by 0.05 to the ns minus 1. Ns was 0.965 or something like that. For that, we have been able to match the m square phi square models, primordial power spectrum. All right. So as you can see here, it is given. Your pivot scalar is given here. Your scalar amplitude is this. That means this is the amplitude at the pivot point, and scalar spectral index is 0.966. Okay. Reionization is true. You are assuming reionization, and you are estimating the reionization redshift. I'm going to discuss that in another notebook. And the reionization optical depth from Planck base fit turns out to be 0.053543 or something like that. This is not needed. Reionization redshift is not needed because reionization redshift for these models are calculated with respect to given a optical depth. Okay, because we are using a tan hyperbolic model of reionization. This is something that I'm going to discuss again. Reionization delta redshift, this you can change and see what is the effect on the angular power spectrum. Recombination model is fast. As I said, that there are different types of recombination codes which solves this recombination equation dxc dt. we are using rec fast here, or you can also use Cosmo rec. It also has Cosmo rec support. They match pretty well. And all right, that's it. So bispectrum is not needed. So what you do in the cam directory, in cam Fortran directory, just say make clean and say make cam. Please do that. Once you are able to do
inside the Fortran directory.
Inside the Fortran directory, yes.
Okay. Okay.
By the way, if you have downloaded Cosmo IMSc from the Git, using Git clone, you have to say -- recursive so that you can download the folders inside cam directory as well. And let me also put another file, upload. Okay, there is some message. Okay, you have downloaded from the GitHub. So you say git clone. Second, git clone recursive. Then the so okay, the git is taken as a caps letter, but it will be small. Git clone, then double hyphen. Okay, again, this is a problem in Zoom chat. Double hyphen recursive, then you give the git address. Okay, please do that. In the meantime, let me just search for the convolution integral. The cam Compilation is done.
Yes, sir.
Okay. Anybody who haven't been able to do that, please inform here.
So inside the Fortran directory, it was make and then what was
Inside
the command?
no, make clean and then just say make cam. You can also say make or make all, but make cam is simply does the cam computation. Okay. Some cam has recently changed its integration. Okay, Arijit, what is the problem? You say I didn't get.
Actually, I'm not understanding what you said. Uh,
Where, what you said? Sorry.
the copy or make file. How to make file there?
You just say you have a console. Okay, let me ask you. You are in the Psi server directory or in the
Psi
Uh,
server, sir. Psi server.
Psi server? Okay, fine. So do this thing. You are able to see this one, right?
Yes, switch to
Switch
Jupyter
to
Lab.
Jupyter. Yeah, there you click console. I hope you are not in my directory. You have copied the directory, right?
Yeah, I am which one? I have copied in
Inside your
INI Pi and COM main F90.
no. What I'm asking is that you have copied my folder inside your directory, right?
Total folder that Dhiraj.
Yes, you have copied, right?
Yeah.
Now, if you open this Jupyter Lab, then you go to terminal and you locate where you have copied the directory. You change to that directory. See, you are able to see that, right? I am in the terminal.
Okay.
Now, let me see what is there in my terminal. So for example, in my terminal, I have this workspace storage. I'm going to changing to that directory. Dhiraj, then workshop ISI, and then Dhiraj, Cosmo MC, cam, Fortran. Just say make clean and make cam.
Okay.
Able to do that?
Yes, sir. Yes, sir. Got it. Thank you, sir.
And also, okay, please do that. Then I'm going to say one thing at a time. Okay. If I increase the font size, everywhere it increases. Okay, that's not a problem.
Sir, did you just upload one new file or a couple of them?
Okay, so let's just go one by one. Let's get this file. I'm clicking and you are able to follow, right?
Yeah.
We just need one file called, I have, okay, inside the cam, inside my cam, Fortran, plotcam.ipynb. You can copy that, or if anybody is doing it inside the inside their own local directory, I can put it in the chat box. Do you prefer that? Let me do it anyway. It is not in the table. This is in the Fortran. TIHISI session, Cosmo MC, cam. Okay. Okay. So this is to plot the cam. Usually, if you do it in your own machine, if you have GNU plot, and then you can simply do that. But I have prepared certain plot. One certain plot commands or plot cells where you can simply run and then import those data.
So I'm facing an error called baseline lens TLS data not found when I'm trying to plot the third cell.
No, that is you have to that is the plotting fly. In order to plot that, you need to what you need is that you need to copy or generate the files. So you need to generate the baseline files. Okay. So in order to do that, you have been able to compile, right? I am not able to compile here. I do not know why. Any driver.o is needed by cam. That is not there. So why it got deleted, I don't know. Cam dark energy initial power. Okay, it seems that it got deleted. Check again. But no worries, I had already created a copy yesterday in my account and I prepared. No. By certain processes, it got deleted, I believe. Certain copying process, etc. I believe you are able to see my screen. Okay.
Yes, sir.
Good. And my screen is now having a console. Good. I am now in the cam Fortran directory. I am assuming now if everybody have been able to compile. What you do, /. Let's just see what is there in the file in the plan 2018.ini. You go to ini files, plan 2018.ini. Just open this file and you will be able to see output root. You just say baseline. Okay, baseline means simple lambda obsidian power law primordial power spectrum model of the universe. Okay, with certain other assumptions on neutrinos, degenerate species of neutrinos, etc. But let's, for our purpose, assume that this is the baseline lambda obsidian plus primordial power spectrum assumed as power. So just write it as baseline.
Sir?
Yes.
Is this the prior, what we setting as the baseline?
Prior means what? Prior
in Bayesian analysis.
No. We
okay.
are not. No, we are not doing any Markov chain Monte Carlo. We will be coming to that.
Okay.
So these are baseline. So this is just a name of your file. Okay, just to understand what files you are generating. All right. What file you are generating now? You see, these are the simple values. These values don't vary here. You just give the best fit values that you obtain from plan and you use those.
Okay.
And the baseline means simply you just say baseline and then run it with cam and then just say ini files. You go to the other directory and then plan _2018.ini. Can everybody run that? Let's do one thing. Once you run this, please post the output inside the chat box. Okay, it doesn't matter how crowded the chat box becomes. I just want how many? Let me check. I just want 39. So if I remove me and Supratik, then there are 37 or 36 participants, let's say. So I need 37 answers. Okay, good. File not found. Init files plank 2018.ini. No. Dot slash. You go to the one.
Oh, okay. Yeah, right.
Yeah.
So the last camp command is showing some values. So do I have to post that values in the chat box?
If you just run it, if you find something, just write it.
Okay.
CD storage, no search for Arijit Panda. Okay. Arijit, I'm coming to you. Rahul, okay. Rahul have been able to generate it. Okay. Steps after compiling camp. But okay, this is Oritra Kundu and Arijit Kundu said. Okay, just a second. Arijit Kundu said that storage. No, Arijit, what you need to do is that you need to locate where you have kept your. You said that you have already copied my directory, right? You have to copy my directory inside your directory. So if you have been able to copy that, you go to that place. Okay. It simply if it said CD storage, that means that your storage doesn't have any. Your home doesn't have any storage file, any file called storage. Okay. You see where you have copied. You can click and see what is the directory structure. For example,
Yes, sir. I have copied it in the storage file. There are two files, temporary and storage.
Yeah.
So I copied your file into my storage and then my directory name Arijit Panda and persistent.
No. Then why are you not able to CD to storage? It is a very simple thing. If the folder is there, you will be able to CD that. Otherwise, do an ls just to see what are the files or folders in that area. Okay. So this is very important, Arijit. Please do that, Asa. Okay. I think Anirban have been able to get that. And CSSC, this is Ornov, is it?
Yes, sir.
Okay. Oritra Kundu, can you repeat the steps after compiling CAM? Okay. After compiling CAM, it is there inside in my screen. As you see, /cam /init files /plank 2018 plank _ 2018.ini. So you are asking CAM to run the Boltzmann equations and compute the CLs using the primordial power spectrum, using all the values that are there in the INI files. Okay, that is the initialization file. So, okay, Nilanjan, they have been able to do that. Is it correct? Anubhav Banerjee, make finish like G Fortran. Yes, if the CAM executable is there, that means it is correct. If you say /cam and run this with the INI files, if it executes, then it is fine. Devarun have been able to do that. Nilanjan Dev, Sangoti have been able to do that. Good. Guys, I just have found 5 or 6, right? I want 36. I am not able to keep track of all of them, but let's wait for another minute before I proceed. Is this just viewing the file or initializing the variable? Viewing the file means?
I mean, this command that I typed .cam.ini file to .ini, this is just to view in the console what the values are.
No. This means you are running the CAM. You are basically running. You are solving the whole set of Boltzmann equations.
Oh.
Everything, photons, baryon, dark matter, neutrinos, everything. You put them together, then you solve them. You get the scalar power spectrum. You convert that, and then you get the angular power spectrum. Okay.
Okay.
Then you do the same thing. All the things are actually done whenever you do this, whenever you run this file. Okay.
So
Can you repeat? It's okay. Can you repeat the command make cam?
Make cam. Here I'm writing here, just like here. Make CAMB.
Yes, should I go to the file directory on the left hand side while entering the cd command?
Sorry, again.
While I am writing the cd command, I am finding the directory. Should I go get also to the my left side there where it is showing the file
No.
names?
That you don't have to worry about. No. That can stay wherever it is there. If your console goes changes to that directory, you will be able to see that directory in the. Okay, let me show you. Yeah, see, I'm highlighting Fortran. Are you able to get that? If you are able to get that, then we are fine. Okay. Okay, Rahul's question I have answered. Or after typing cam, permission denied. Are you running in my directory, by the way?
No, I am in my directory, I think.
In your directory, how can permission denied? How can you be denied permission?
No, that was not by me, I think. Permission denied is Orithro Kundu asking about.
Okay.
I am Orijit.
Orijit, oh, sorry. Orithro. So do a PWD. See what
Sir,
is.
I am also getting the same.
Do a PWD, and see what which directory you are in.
So I am still stuck in the cd command.
Okay. Do you have a Windows or a Linux system or a Mac system in your machine?
Windows 10, sir.
Windows. Okay, that is going to be a problem because in that case you need Mingu. Okay, Orithro is in your his own storage on Kit. Okay. After make clean, then what are the steps? Make clean, make cam. MAKECAMB, all small. Workspace storage on Kit, persistent CMB cam, Fortran. Yeah, then you should not be denied of the permission. Do something like this. ch own. Okay, sometimes this cam. Once you compile, just say ch own cam. Onto this, sir, my case, I'm getting the same error. No rule to make target any driver needed by cam. Okay, this is okay. Something okay. The thing is that this is not my doing. While what I did is that my workspace ISI have been given the permission to everybody, read and write permission to everybody. So somebody has deleted that INI mistakenly. So that is why you are not able to get that. In any case, let me do something. It has worked for whom? It has worked for Anubhav. Good. Let me just give you the ini driver.f90 because I cannot also compile, as you can see. So that it's good that I had a backup. Fortran ini driver.f90. I am sending you in the chat box. Okay, please download that, or let me see if I have that backed up in the workshop ISI as well. Workshop backup. Cosmo MC can Fortran. Okay, you can also either you can download and put it there, or you simply copy this ini driver.f90 in the sci server inside the Fortran directory from here to your directory. Let me now make cam here. Okay. No rule to make target ini driver. Yeah, so I have already fixed that. You just download that. Either you download it from the chat box or you download it from the Psi server itself. Okay, while it compiles, let me just explain the things. Once you have run this, you will see according to your whatever the file name you have given, output root, your files will be created, your CLs will be created. As you can see, can you see my screen? Baseline, matter power, baseline, params, baseline, scalcls.dat, all these files. Are you able to see that?
Yes, sir.
Baseline lensed CLs. Good. Let me just do it in the G Fortran. I'm going to show it very quickly, and then I'm going to move to the notebook. Now you see, just check what is there in that file. Less baseline lensed CLs .dat. So this, the first column is L, from quadruple to, if you go down, 2600. It is plotting. The second column is CLTT, L into L plus 1, CLTT divided by 2 pi. So this is called DL. In the Planck paper, you will find it to be defined as DL. Then the next one is EE autocorrelation, the polarization, E mode polarization. Third part is the BB. We haven't given any tensor to scale ratio, but BB comes from the lensing of E modes. And there is T and E cross correlation. All right. So resend it. Ishita, you are working with your own machine, or you are working with your Psi server? Parallel question to other people who have not been able to. Okay, Psi server, it is there. You just recopy the any driver.f90 from inside my Psi server's cam Fortran folder. And for others who had problem with this make, where unifile was not found, please do that and have you update me whether you have been able to get it and make it again. Okay.
Sir, I'm not getting any baseline. This baseline means. CLS.
What are you getting? Are you getting anything called Planck _ 2018 _ lens?
Oh yeah. Okay.
So that means that you have not changed your output root as baseline.
Baseline. So, okay.
Yeah, baseline is the name of the file. So since I wanted to be uniform so that everybody gets the same thing, I wanted to be sure. So that's why I changed the file name as baseline. Okay.
So now do I have to open this Planck 2018 lens?
Do one thing, please do it as baseline. Okay, so that it becomes uniform. Otherwise, if you say it Planck 2018, other people will be confused. Okay, do it in the baseline.
So how to change to that baseline, sir?
In the ini file, Planck _ 2018.ini, open that. In that file, output root, the first entry will be output root after 3 or 4 lines. In the output root, instead of Planck _ 2018, just say baseline. That's it. Okay.
Okay.
You can use any editor you want. Okay. Now I'm plotting, let's say baseline _ scale lensed with line. Are you able to see my GNU plot?
Yes, sir.
Okay. So this is the famous angular power spectrum from CAM. Let me put set log x. You can compare it with the lecture notes. This part is ISW from 0 to 5 or something like that. After that, there is this. The first part is integrated Sachs-Wolfe effect. The second part is the Sachs-Wolfe effect. Then there is this baryon acoustic oscillations. Then why these oscillations gets damped away? I want answer from someone who didn't have any CMB exposure before and learned from the lecture yesterday. why there is an exponential decrease in the peaks. Anyone who had followed the lecture yesterday and didn't have pre-exposure on cosmic microwave background? Please write or unmute and please tell me. No. That at higher L, the amplitude decreases twice. No. 2 by twice L plus 1 is the cosmic variance. It says the CL has an inherent uncertainty because for each L, you have only twice L plus 1 M's to sum over, because you remember the field, the delta T or theta field have been, we have been able to project onto a unit sphere using spherical harmonics. So you have this ALMs for each ALM. So ALM, you are summing over L and M, right? And also you are summing over L to get this theta. That is the expression for the theta field. The variance, this variance comes because for each L you only have twice L plus 1 modes to sum over. So that is why the problem occurs. That this is some kind of an error inside the on top of the theory. Even if you can put your instrumental error to be 0, let's say I can detect up to 0 Kelvin, there is no short noise or any type of instrumental errors inside my instrument. Even in that case, there will be an inherent uncertainty that is called this cosmic variance, and the error associated to that is called cosmic variance error. All right, so it is square root of twice, the error is square root of twice by twice L plus 1 times CL. CL is outside the square root. Now, anyone else, why the amplitude decreases as, so this is the theoretical curve. I am not plotting any uncertainty. Why at higher L this decreases? Can anybody say? Let's go back to the lecture again. Here. Now, can anyone say?
It is diffuse damping.
Exactly. This is the diffuse damping tail or the self-damping, because photons, because our last scattering surface has a width, and in that width, while the photons was getting decoupled, it was still interacting with the electrons. So the signals that it was carrying was getting destroyed by all this kind of interactions. And that is why at small scale, depending on the lambda d, remember the lambda d is the length scale the photon traverses within a Hubble time at the decoupling epoch. So it is exponential minus k square by kd square, where kd is inversely proportional to lambda d. All right, good. Now let's go back to here. Go back here. This is the temperature.
Sir, I had a question regarding cosmic variance. This uncertainty is due to the fact that we have a single universe, or due to the fact that we have a single sky?
If you have infinite universe to, if you have had measured, if you could put your satellite to a different point in the space, there also you could get infinite number of maps, right? Then you would have infinite M's to sum over there as well. So we can only observe one universe from our place. Okay, so that is why we are not and that is why if you get the one map, then at large scales you can only have just twice L plus 1 modes.
Okay, so that means if I put a probe like Planck in different galaxies, hypothetically, will we be able to decrease the variance?
Yes.
So that means the problem is due to one sky and not one universe, because the universe is one. We have access to just one universe. But when I put different probes, I get different skies.
Yeah, it's called the ensemble average, right? If you are able to have different maps, you will be able to get the ensemble average of from different places. Okay. But since you have one map, you only have limited scope to average it.
Right, of course.
Sir, can you please repeat the command for the power spectra plotting?
Oh, okay. So you can use any command. For example, it is you have to plot this lens cls.dat baseline underscore lens cls.dat. You have to plot the first column against the second column. First column will be the X and second column will be the Y. Now I'm going back. Yeah, I'm going to the notebook. Okay, I'm going to show you how to do that. What I am doing is that I am just using a GNU plot. See, I'm going to the GNU plot and I'm plotting baseline scales. Oh, sorry, should plot it with. Can you observe any difference here? Difference between these two plots? Let me make this a little bit wider. Can you observe any difference between these two plots?
Yes, in the higher L, it's a change.
Yes, at higher L's, there are changes. At lower L, they're exactly the same. At higher L, it changes. This is the effect of lensing. One, I have plotted the without lensing. This is without lensing. And this is what I have plotted with the lensing. WMAP had detected up to L equal to 800. So that means up to this point. Okay. This is 900, I think. So this is, okay, let me check. I'm not able to see this. 600, 700. Yeah, this is 800. So WMAP have been able to detect this here up to here. And the error bars here were huge. So it didn't matter whether you calculate lensing and compare with the data. WMAP was not able to detect lensing. But when Planck came, you see there are so many acoustic peaks from where you can see the lensing effect. You see, I'm just enlarging that and you will be able to see in greater detail. So lensing smears the peaks. You see, these are pronounced peaks, the green one. What happens is that if you add lensing, it mixes the multipoles. And it basically, so you just see what happens. You have if there is no rain, you are looking out your window. All the structures that you are seeing are correlated, and you are able to see a building. Now, rain comes, and your glass window has some rains in it. And because of the raindrops, the raindrops are actually what it is doing. It is lensing the light rays that are coming from the building against you. Opposite to you. So what happens is that the buildings gets distorted. The sharpness of the building gets distorted. So this is what is happening. The signals, the sharp signal gets smeared out. So the peaks comes down. Okay, the TROS also goes up a little bit. Okay. So this is the effect of lensing that I wanted to discuss. Now let me go back to the Jupyter lab. So yeah, plotcam.ipynb. Have you been able to copy that in your directory?
Yes, sir.
Okay, good. So if some of you have not been able to copy that, let me tell you again. Inside my directory, bingo cam Fortran, there is a notebook called plotcam ipynb. Copy that in your directory inside the Fortran directory. So you can simply at your time after this lecture, you can copy all this to your local directory so that you can do this works yourself. High L extrapolated template lens potential.clc is that file. You have to get that. You have to get it should be there. Then your tar was not been done successfully. Go to CAM. I hope you are able to see my screen. I am inside CAM. Then Fortran. Then high L. Where is this high L? Yeah, CAM. Yeah, here. You can simply download this one. Okay. Resume share. Why my screen sharing have been paused? Are you able to see my screen or no?
Yes, you can see.
It says your screen sharing is paused. I'm saying resume share. I'm not able to resume share. Stop share.
And we can see.
Okay. Now I hope it is back. So who was having this problem? Anubhav, I guess. High L extrapolated template lens potential CLs.dat. You just download this one from the CAM Git or Cosmo IMSc Git. Okay. Good. Let me open the chat box again. The plot command is showing PL command not found in the sci server. No. Sci server doesn't have a GNU plot. Actually, I have not been able to find the path to the GNU plot. So use this file. Use the GNU plot was what I was using is that in GNU plot I was just trying to show you very quickly the difference between lensed and unlensed CL. Now I'm going to the different topic, and I have already provided you the plotting software, the notebook. So just get the plotting notebook and then open it with the Jupyter Lab. Okay. So you see what I'm doing is that I am actually loading this file baseline lenscls.dat that you have already computed using CAM, and this has 5 columns: L, DLTT, DLEE, DLBB, DLTE. Okay, so I am defining them as baseline TT, base EE, base BB, base TE, and I am plotting them here. Have you been able to plot that? Have you been able to run this notebook?
I'm having a problem in the 6th cell. I'll show you the error in the chat box.
Sorry, I'm not. Your voice is broken. Can you say again?
So in the 6th cell, I'm having an issue.
Sixth cell. Which one? Okay. 1, 2, 3, 4, 5. No. Sixth cell up. No, sixth cell is with for the dark energy. You have to plot
Okay.
up to 5. Okay. Dark energy. I'm coming there. Okay. Okay. Good. Anirban, you got the plot. Anybody who haven't got the plot? I'm waiting for others because it is better to have everybody in synchronization. Otherwise, if some students are left out, I move too fast with the plots. It might not be good. Okay, got the plot. 1, 2, 3, 4, 5. Let me check how many are. Is there 36? Please. I mean, 5, 6, 7. 36 versus 6. Is it a good number, you think? Make CAM no to make target. Make target CAM. Where are you doing? Hey, you cannot do it in Dhiraj. I mean, sorry, if the Dhiraj folder you have copied, and I understand, but you have to go to Fortran or Git. In CAM Fortran, you have to change to that directory. Or is it? Please do it fast because you cannot. I mean, stuck in here so long. I am telling you repeatedly, telling everyone repeatedly that you have to go to the Cosmo IMSc CAM Fortran directory. You have to locate where your Cosmo IMSc directory is. Okay, probably 10 people have written. Please, at least 20 people. at least 20 students. I mean, why I'm stressing, because you see, I mean, what I'm doing is that you, I mean, I'm while teaching you, I'm trying to teaching the theory, I'm trying to make everybody move with the softwares, codes, so that when you try to do your own thing in your PhD, you will not get stuck. Inside server, after writing the command make comp, hey, make comp, no, it's not make comp, make cam. What are the commands? /cam /in ini files .blank _ 2018.ini. I'll move
Sir,
to that.
here,
Yeah.
hello?
Yep.
Sir, this base TT is basically L into L plus 1 CLTT by 2 pi.
Exactly. This is the DL. This is the definition of DL. Okay.
DL. Okay.
Actually, everybody till Planck used to write L into L plus 1 CL by 2 pi microkelvin square. So whenever I was writing paper, I was also doing that. And then Planck found this way of DL, and then everybody was thinking why people haven't done it earlier. There is just a redefinition of parameters, right? Okay, good, Vaswati. This is what I wanted, right? That's good. Then see, what are the files? Are you getting Planck _ 2018 or baseline _ baseline _ do an ls and see what are you able to see? There will be new files generated, and those files will be written as sometimes something like _lenscls.dat. The prefix should be the either baseline, if you have been able to change the output rule in Planck 2018.ini file, or it will be Planck 2018 _ lenscls.dat. Okay, but I would urge you to make the change from Planck _ 2018 inside the output root, inside that file, out from output root baseline, from Planck 2018 to baseline here. Any files? Okay, so no, this is not what I want. I want to see this. Any files? Planck 2018.ini. If you open that, you will see that output root. I hope you are able to see my screen. Output root. Instead of Planck _ 2018, write it as baseline, BASELINE, then save it and run this /cam ini files Planck 2018.ini again. Once you do that, please open the notebook. Here is the terminal screen. Use VI, or yeah, just open the file from the left pane of Jupyter Lab, edit it and save it with Ctrl S. Yeah, that will work as well. Okay, so I assume that everybody have been able to do that, right? Okay, so now go to INI files. Just copy this file to this file, planck 2018.ini to planck 2018 wde.ini. Do it, please. Planck 2018.ini to planck 2018 wde.ini. Then open this file. After copying, open this file. Planck 2018 wde.ini. We are going to see the effect of dark energy equation of state. In the output root, write WDE. Okay. W dark energy. Very simple. Come down and here effective equation of state parameter for dark energy. Instead of -1, write -2. So I am going for the phantom dark energy. I'm leaving my console open for 30 seconds. In the meantime, I would like all of you to follow what I am saying. Copy your planck 2018.ini to planck 2018 wd.ini. Step 2, change output root from baseline to WDE. And step 3, effective equation of state parameter for dark energy change from W equal to -1 to W equal to -2.
Sir,
Yes.
so we can't find the WDE file. If you see the chat box, I'll tell you which files I'm getting when I do ls in INI files.
No. You have to copy that. You have to copy the planck 2018 to planck 2018 underscore WDE.ini. You have to create that file. Just copy CP planck underscore 2018.ini planck underscore 2018 underscore WDE.ini. Just create a copy of your own old file. That's it. Then you change that.
Sir, I can't find that file.
No. If you do this thing, CP, how do you copy something in
No, I know how to copy, sir, but from where to copy? I can't find the file original file.
It has to be. Come on. If you have been able to copy, if there are no errors, their file should be there. Change the directory to ini files.
Yes, I am in any files.
Okay. So planck. Yep. So you have copied, but when you do ls, you are not able to find it.
No, I'm only getting parameters 21 centimeters and param count, param lensing, planck 2018 ACC, planck 2018, and source defaults.
Show me the CP command that you have given.
I am doing ls in INI files, and I'm getting this.
You have to copy. You have to copy.
Okay.
That is what I am telling. No?
No, sir.
Type this one in.
Do I type this in the INI file directory?
Of course.
Okay.
This is how you copy.
Okay.
That is what I was telling you. That this is, you are copying one file to another file. You're just making a copy of that. because you want to keep the old original copy of the file preserved. Now you are making changes in a new file.
Now I get it. Sorry, sir.
Okay. Any one student who have not been able to do it, please write it immediately. All right. Open Planck 2018 WDE.ini. Change output root from baseline to WDE. Change W from -1 to -2, the one that is highlighted in my screen. Going to wait for 30 seconds. Guys, you can make errors. You can make hundreds of errors. Please write it. If you are making errors, not able to proceed, please write it. If you are finding it difficult, please let me know. Okay. Now I want in the next.
We have to change W from -1 to -2. I mean omega from -1 to -2.
Not omega. This is W.
So W from -1 to -2.
Yeah, -1 to -2. Once you do this, go to your Fortran folder, then run cam again with this file. Instead of Planck 2018.ini, run with Planck 2018 WDE.ini. Run it, and I want 36 messages here with the answer. Okay, there are 36 participants now. So I want, okay, 35 people are, okay, disappearing. Too hard? So actually 33 messages at least. Okay, or no, good. Good. Bhaswati, you said that, sorry to say, sir, there is no file name Planck 2018.ini. You have yourself run this cam just a while ago with Planck 2018.ini. So it is not possible that you don't have this file. Go to INI files in the parent folder. From Fortran, change to INI files. But you should say this when I am saying that whether you have been able to copy this file or not. Devarun, Onirban, Oritro. Okay, Yashi, please write the output of the files, output of the command. You've got it. Okay, 9. Anyway, let's proceed with that. So I hope that while I'm discussing this, others will be able to run, and the outputs will keep coming. Now, this line. In the notebook, this line. Now I am using a different equation of state of dark energy. I'm running the program and I have got the outputs. Now I'm going to compare these outputs. What did I say? If you have the dark energy at large scales, there will be changes in the at large scales. There will be changes in the CL anisotropy spectrum, in the temperature anisotropy spectrum, because the ISW effect is going to change. So the ISW rise is going to decrease if it is phantom. If it is, it will be increased if it is if W is more than -1. And also the distance to the last scattering surface is going to change, because W changes. Remember, I have discussed distances in that notebook. There is a provision to change the W. Okay, I think the old one didn't have the one that I've given in the as distances. Just check whether you can change W. If you don't have, then you have to include that. If I have used lambda CDM, then W is set hard coded to be -1. Then that is somewhere, that is where you need to change it to W equal to -2. If you use -2, of course, it is not just W equal to -2. You have to also see what is the formula for the distances. If it is not written that includes the W, then you have to include that. Therefore, if the distance to the last scattering surface changes, then the distance of where the acoustic oscillation peaks, or the scales at where the acoustic oscillation peaks, also will change. There will be lateral shift at the acoustic scales and scales smaller to that. Are you able to get this plot? Okay, good. You are able to get this plot in the Python notebook, right? There should be 33 yeses. Good, good, good. At least there are 12 yeses. Should I move to the next topic, or you want me to stay here a little bit more? If anybody wants me to stay here, please let me know. There is no shame. If you are slow, no problem. Let me tell you, when I code, I am extremely slow in coding, but I try to do it right. So I have many questions, and I Google it. I try to understand it. Okay, okay. After changing the output route to baseline. No, that is for the baseline. Now we are doing WDE. So if you are stuck there, no, output route to baseline, you have already done it, right, Vaswati? Basuti, can you unmute yourself and speak to me?
Hello, sir.
Yes. Let me ask you
Hello,
a
sir.
few questions. Once you have done, you got the results Planck underscore 2018.ini. You have changed the output route to
Yes.
base to Planck 2018 to baseline. Then you have run that command again.
Yes.
/cam ini files. This one. Oh, let me just. This one. Have you been able to run
No,
this?
I haven't done this part.
You
No,
have
no.
done-
Actually, there was connectivity problem. I lost the connectivity, so I came a bit slower.
No problem,
that's
no
why.
problem. I mean, don't worry. If you have missed something, you can do it right now. /cam //
Okay,
initial file Planck 2018.ini. If you have changed the baseline, run it again. When you run it again, do
Okay,
you
sir.
get this?
Just a moment.
Yeah. Anybody else is having any problem now? Please speak up. Speak up.
Sir,
Yes.
so the compiler is saying this WD less CL dot that not found. So why? I don't know.
Okay. Then what did you do prior to that? How did you run that command? This command.
Yes. I've run all, all the comments. Yeah.
Okay. Check what is the output route in Planck underscore 2018 underscore WDA.ini. What is the output there? While he finds it, please others, please, if you have any other questions, please speak up.
So it was not a baseline. It's Planck 2018 only.
No, you have to put it. Okay. So if you're running for baseline, if W equal to -1, if you haven't changed anything, their output route has to be baseline. If you are changing it to be W equal to -2, -1 to -2, by changing this file, by making a copy, then you have to put W equal to -2, and then output route will be WDE. So there are 3-step processes. First, locate the file.
Okay. So I have changed now to baseline. So this output route.
What is your W?
W I have given -2 now.
No. Then this is not a baseline. Baseline means lambda CDM. What is the okay? So what is the equation of state for a lambda CDM cosmology? Where you
W is -1. Yeah.
-1. So your Planck 2018.ini, that has to be run with W equal to -1. Its name will be baseline.
Okay.
When you run Planck underscore 2018 underscore WD.ini, after making this copy, you have to say W output route equal to WD and W equal to -2. You are changing the equation state. So there should be 2 files. You see?
Okay, sir.
I'm showing you my directory structure. This files. Sorry. My ini files has these 2 files. Okay, you don't have to worry about any other file. Planck 2018.ini, where I have set it to be baseline. I haven't changed anything else apart from the fact that I have changed this output route from Planck 2018 to baseline. And I have copied the same file step 1 Planck 2018 underscore WD.ini, copied the file from here to here, opened this file, made the change where it is written output route equal to baseline, because I had already changed it to baseline. Now it will be WDE. Now instead of W equal to -1, I put it -2. Okay.
Yes, and now it is running. Yeah. Thank you, sir.
Okay.
So okay. Yeah.
Okay, and then Anubhav Banerjee says, what does initial power spectrum in Planck 2018 file means? What does happen if one tweaks these parameters? Okay, good question. I'm going to show that. I'm going to answer that. What is this error? File not found. Any files? Can you show me the file structures in the any files? Means that go to INI files and do an ls and show me what are you getting. Can you hear me? This is for Bhashwati. No, you have to go to any files, INI files. You go to INI files, not here. CD to INI files.
I am in INI files.
No, it is INI files doesn't have this. You are in the Fortran. I can see that.
Okay. Sorry. Okay. CD INI files. Yeah. It is showing no such file or directory, but it is showing there is a folder called INI files.
Yeah, but it should be. It is not in there. It is in the parent directory. CD // INI files as Arnav is showing. Let's do that.
Yeah, it's working. So I'm getting this as ls.
In the ls.
Yeah.
So your Planck 2018.ini is there. Then I asked you to copy it from Planck 2018 to Planck 2018 _ WD.ini.
Without making any changes?
Yes. But if
okay.
But another thing is that if you are running with Planck 2018.ini, it should be there. When you say /cam, it says Planck 2018.ini file not found. I do not know why this is showing. This shouldn't show.
Yeah, it's copied.
Okay, so I'm showing it once more before going to the next topic.
Okay, thank you, sir.
Yeah. So for all others who are stuck at this level, I am assuming everybody have been able to get the baseline. Now I am doing the changes in the dark energy. I have copied that file. So this is my directory structure. See, cd./ini files. This is my directory structure in the ini files. Okay, clear. Okay. This is my directory structure. I have, okay, let me do as many ls as possible. Okay. Planck 2018.ini and Planck 2018 _ WDE.ini. If you make a copy from this to this, you just open this _WDE.ini. In the output root, change baseline to WDE. You don't have to do Vim or VI or anything else. You can simply open it with anything and then Control S and do the GUI and anything will work. And then just come down here. Dark energy. Okay. From -1, you make the change to -2. Then go to cam and run cam. Sorry, go to Fortran and run cam.
Are we making the change in co-moving sound speed? Or
No.
equation of-
W.
Okay,
Just
okay, fine. Okay.
plan 2018 underscore WD dot. You should get this. Why temperature changes because of changing WT? Oh, why it changes? Because the spectrum changes means that there are two ways. One is that your gravitational potential, okay, that is given by this phi and psi, right? So I have shown you in that notes, I have shown you there are three terms when you calculate the theta. One is the Sachs-Wolf effect, another is Doppler effect. Let's just talk about Sachs-Wolf. One is Sachs-Wolf effect, which is related to the phi plus psi. That means the gravitational potential, which is same in the matter dominated epoch. Let's say it changes from 9/10 from the radiation to matter dominated epoch, and this phi is obtained from the primordial power spectrum. Okay, so because that is the quantum fluctuations that gives you the phi. That is a part that is nearly constant. It just follows the primordial power spectrum. Then there is this integrated Sachs-Wolf effect where there is this phi prime and psi prime that gives you an enhancement at the large scales. Because of it changes from matter dominated to the dark energy dominated. If you change the dark energy equation of state W, the distances changes and the integration that you are doing that changes. There, it changes according to your equation of state. Also, that is the large scale effect, and the small scale effect is that what your distance to the last scattering changes. If you okay, so it will be clear when you talk about dark energy, but we have talked about distances, right? A distance to any redshift. The distance to any redshift that we had calculated till now in my notebook that I had circulated was assuming W equal to -1. If it changes, then the distance to any redshift decreases or increases depending on your W. That means how much acceleration that you have obtained using a W greater than -1 or less than -1. Depending on that, your distance to the last scattering surface increases or decreases. So all the peaks that you are seeing are laterally shifted backwards or forwards. Is it clear? That is what I am showing in this plot, in these two effects. One is at the large scale effects, low L, and one is at the intermediate to small scale effect. Now, there was another question on the initial power. So I think that was made by Anubhav, right? Okay. Initial power, if you change that, I am not going to ask you to do that. Let me just show it to you quickly. Fortran CD INI files. Now, let me just change to SCP plan 2018.ini to plan 2018 amplitude.ini. Okay, plan 2018 amplitude.ini. Let me just write it down as amplitude. Okay, and what I'm going to change here is coming here, scalar amplitude. This is what Anubhav you are asking, right? I'm making it 3. Okay, good. CD double dot CD Fortran. Okay, let me run cam amplitude.ini. Okay, let me see what I get. Baseline length CLs with line with 3, amplitude lens CLs. In one case, I have made the amplitude from 2 into 10 power minus 3 to 3 into 10 power minus 3. Can you spot the difference? What did it do? Can you tell me? Can anyone tell me what happened? Good. The normalization change. So the overall amplitude changes. If you change the NS, the tilt will change. Okay. So very simple, because you are multiplying the power spectrum with the transfer function. So it is simply, there will be one change. Of course, there will be a tiny bit of difference because of the lensing. Okay.
Excuse me, sir.
Yeah.
Sir, a lot of parameter are generated. Like if you change one, it will change another parameter. So how we are changing like freely all the parameters? Will that cause a problem to us in like, or something like they are not dependent on each other parameters?
They are dependent on each other. They are okay. So you shouldn't ask this question that whether they're dependent. You should ask the question whether they are correlated with each other. Means that one effect is correlated with another or not, right? So dependent means that when I say NS and AS, they are not dependent on each other. Amplitude is just changing the amplitude, and tilt is just NS just is changing just the tilt. So they are not dependent on each other. Whether they are going to give similar effects in the primordial, in the angular power spectrum, that is different. That is something that we need with we need to get the correlation. That is when we do data analysis. Okay. Okay. Let's now. Now I'm going to the reionization part. Before I go to the reionization part, let me just show you one effect of reionization. Okay. Here. Reionization optical depth is the okay. Let me, before going to that, let me cover another part that is here. Okay, the difference between the baseline and WD is plotted here. Okay. Anyway, you can do that. Now, another part is that the electron fraction. Yesterday, I promised that I am going to show you how the electron fraction changes from very early universe to the recombination epoch, and from recombination epoch till today. So these are the, if you remember, how does one choose the initial starting values? Okay, yeah, I'm going to finish this and then you can ask this question. Please remember, okay, I'll take this question at the end. Okay, so please remember your question and please ask me this question later. Okay, now this is the scale factor when the universe was very small, 10 power minus 8, and this is today. Okay, scale factor is 1. So when we were in thermal equilibrium and the electron was kicked off by the protons, there were everything was ionized. The electron fraction is 1, but it is more than 1 because the electrons are coming. Electron fraction with respect to neutral hydrogen atom. That is why what we basically parameterize. It is x equal to Ne by Ne plus Np. So, but there are there are more electrons than the electrons from the hydrogen atom, because we are getting electrons from helium as well, helium first and second ionization. So it is depending on the primordial helium fraction, it comes out to be nearly 1.16. So 16% there is extra electrons with respect to the hydrogen atoms. and then it becomes constant. It stays constant until the time when the universe temperature drops and the recombination happens. So the recombination starts, and at some point of time it falls below, electron fraction falls below, okay, and then it goes very close to zero. We are going to see that in log scales. And then when the structure formation starts here, it again starts going up, and then again so the ionization of hydrogen is completed here, and the first and second ionization of hydrogen, first state of helium, first ionization of helium happens here, and then the second electron comes from this another helium ionization, and then it becomes 1.16 again. Okay, so this part is recombination, the left part, the right part is reionization. Same thing I have plotted in log scale with respect to Z. Okay, this is with respect to A, and this is with respect to Z redshift. So you can see it falls below 10 power minus 2, it goes to 10 power minus 3. This is what we discussed, right? The solution to the ionization equation falls below 10 power minus 3, 10 power minus 4. Then structure starts to form when the redshift was around 10 or something like that. And then UV ray from the structures comes out and it starts ionizing. Starts ionizing, then it's completely ionizes the universe. Okay, this is the optical depth. Now, optical depth of reionization is basically the integration of the xc of Z, the area under the curve, over the redshift or over the line of sight multiplied by the Thomson scattering cross section. Okay, so this is a line of sight integration of the free electron fraction. What happens is that the photons from the from this xe, the photon scatters of these free electrons that are free during the reionization, and it gives you a signal on the polarization power spectrum. We are going to see that. If you change, and again, remember there is a visibility function. So if your tau changes, your optical depth changes, overall scaling of the overall amplitude of the temperature and the polarization power spectrum increases or decreases. If you just change the history of reionization, let's say it is whether sharp, it is very sharp, or it is shallow, it happens very smoothly, that changes only the polarization. We are going to see that. So here, optical depth is here. What I'm doing is I'm changing the delta redshift 0.5 to 2. So delta redshift means that I am changing the redshift width of the transition, and earlier it was 0.5, I made it 2. Okay, let me check. It is done. So let me see if I'm plotting here. I'm plotting EE data. Okay, so it is the third column using 1:3. So I would urge you to go through this once the lecture is over, once the session is over. 1:3. You see, at very large scales, there are changes. After that, one falls on top of each other. They become exactly same. Are you able to follow that? I'm going to smaller scale. I'm just moving my cursor. I'm just going to the smaller and smaller scales. Are you able to follow that? Please write down. Are you able to follow my plot? Now I'm going to the large scales, means that I'm going to the low L's. Are you able to follow that? Please write down. Yes, yes. Okay, good. So I have changed the reionization history, keeping the tau same. That means that I was sharply reionizing. Now I am reionizing in a much slower pace, but from much earlier time. So that what happens is the polarization signal changes, but every other signal remains the same. You can plot. So 2 means if you plot the temperature power spectrum, no changes, right? At very large scale, there is small change. That is because of the visibility function changes as well. Otherwise, they fall on top of each other. All right, so let us see what we can. Here you are changing the width of the reionization. Yes, I'm changing the width of the reionization. Good. Let's see how I'm changing the width. For that, okay, so you can find all this in the reionization.f90. Yeah, reionization XE. It is using a tan hyperbolic shape of the reionization. Okay. Also in the results.f90, so the plot that I have shown you here, just a second. What happened? Yeah, that plot I have shown you here is from CAM, from running by my run from CAM. What I have done is I have simply gave a results. PQ, MNO, PQ or results. Yep. Here it is calculating in the results.f90, it is calculating the XE as a function of scale factor. What I did is that I just printed a write command. So it is calculating all the electron fraction from very early universe, let's say 10 power minus, when the redshift was 10 power, scale factor was 10 power minus 8, when redshift was 10 power plus 8, and till today. So it calculates from the reionization to, from the recombination to the reionization. Okay, so it covers the whole epoch. So from here you can get that. I just wanted to show you the place. Cool. Now let me, so I have plotted that, and I have generated that file, and I have plotted that. And then let me go to, so this file cmb-tau.ipynb. You will be able to download this file, or again, if you remember, sorry, what did I click? This is in the notebooks folder of my Sci server folder. I have copied it just now, or you can just use your computer and use these 3 files. The main file is cmb-tau.ipynb. Are you able to open this file? If you can open this file inside the Sci server, that is also fine. You don't have to run this, but just have a look at this. Okay. because we don't have that much time. Okay, I got a Slack message. I tried to download. After it got downloaded 320 MB, it resumes from the start. Can you tell me what else I can download in the safest way? Okay, this is something that I haven't encountered. So whoever has written this, reply from MJ. So whoever has written to me this thing, I think others who have downloaded this can help you with that. Okay, because it must be some problem with the server. Okay, time up.
Sir, I have a
Yep.
I have a question. Yeah, if we change the deionization history and recombination history in both the cases, optical depth will change.
This optical depth is only computed for the reionization. Okay, so we are integrating from, let's say, 0 to 70 or something like that. Then after that we are not integrating. If we integrate from 0 to 10,000, then recombination will come again. Okay, but this is the reionization optical depth. This tau is only for that. Okay.
So, sir, if we change the recombination history, then this will not, optical depth or reionization will not change.
It will not change. If you change recombination history, what you will find is that you will find changes in the acoustic peaks. I mean, because it is an early time, so the modes that entered the Hubble radius at that time will feel the changes. Okay, so the more earlier you make the changes, the more earlier history you make, you alter, the higher L's will be affected. Okay, so for example, dark energy, you understand what is happening in the dark energy. I have changed the distance to the large scattering surface, so all of them peaks gets shifted, right? So I am changing the history to the if the distance changes, all the history changes, because the distance to any earlier point gets changed. Now, okay, Rahul is asking, how do we make the free electron plots in the XC.5? Yeah, I showed you. I'm writing in 4.10. I'm in that results.f90, and then I'm just copying it as XC.dat. Okay, good. Any other questions? So I hope that now you have been able to open these 3 files in your desktop or in the Psi server. Anyone who haven't done it, please let me know now. I need to proceed a little bit faster. Good. So we are going to discuss tan hyperbolic model of reionization, optical depth, neutral hydrogen data, and constraints. Neutral hydrogen data is something that Professor Tirthankar Raichaudhuri is going to discuss anyway, or he have already discussed this, so I am not going to go to that. But this is important because I am going to use that here. Neutral hydrogen data means basically how much neutral hydrogen you have at different redshift using different probes. Okay, Lyman alpha forest, etc. Lyman alpha emission. There are different probe, gamma ray bursts. So for reionization history, you can have a look at these papers, Bowens et al., which has the updated means after Planck 2013, the updated constraints. Then Wayne Gill Holder, who had this PCA form of reionization, and then you can see my paper, Hajra Smooth 2017, where we had discussed this polyreion model of the universe, which again after some time was altered, made more flexible, and named as Flex Knot, and was used in the Planck 2018 release. Okay, you can see now that I'm just defining the redshift here and XE. Okay, XE from age, I'm defining it here, defining it like this. XEZ equal to 1 plus 1 half times 1 plus tan hyperbolic Y Z reionization minus Y divided by delta. This is the width of the reionization. Okay, this is what I was saying that I am changing. YZ is equal to 1 plus Z whole to the 3 by 2. So dy comes as 3 by 2 1 plus Z to the half times delta Z. So this delta Z I changed in CAM from 0.5 to 2. Okay, I hope you are able to follow. So this is the tan hyperbolic model of reionization. Let me just compile all this. XZ I've just written as this tan hyperbolic format. You see, I'm defining dy, defining dXE. So here it is only dependent on A, the redshift, I mean scale factor or redshift, delta Z or ZRE. ZRE where is when your XE is 0.5. The reionization redshift when you are halfway during the reionization. So then you can calculate this XE from helium. This is also assumed to be tan hyperbolic format, and then you add them. Okay, XE from hydrogen and XE from helium, and depends on the helium fraction. There you have to compute your primordial helium fraction YHE. Then you have to convert that using the mass ratio between helium and hydrogen, and you compute that. If you plot that for some value of tau, etc., for some value, for example, for ZRE equal to 6.5 and delta Z equal to 1, you find it like this. This is the history, one particular history of reionization. Now, from the CMB, we can get a summary constraints on tau. If you just plot the baseline values, if you run the baseline values, you get the constraints on tau. Let's say now I'm saying this is my constraints on tau. Okay, this is a baseline constraints. We should not use that exactly to constrain any other model of the reionization, but let's assume that this is a constraint that we have got. Okay, now I'm going to discuss how the Markov chain Monte Carlo works. Okay, I'm not going to discuss in detail, but simply you have defined. Okay, so what I'm doing that I'm defining different quantity A squared times H of Z. I am also defining the dark energy equation of state. You see. Okay, so we can discuss in this in great detail later. And now omega DE I have defined omega dark energy. This is an integral of the equation of state integrand, which I have defined it here. D eta, the conformal time, and then eta you can get it from here, and d tau dz, the integrand of which you can integrate to get the tau. So this is the d tau dz, the line of sight integral. Okay, so let me just compile it here. Sigma t times Ne, the electron number density that can be obtained from the electron fraction. So proton density today, as you can see here. So what I'm doing is that XCZ times the proton density today. I'm multiplying that. Sigma Thomson scattering cross section. I'm then changing the kilometer megaparsec to one particular unit, and then I am integrating that, integrate Romberg to get d tau dz. All right. Now it comes to the non-trivial step. You see, now we are basically doing a fitting. Somebody asked me what is the prior. Okay, so for a very simple chi-square definition, it is simply sum over of all the points data minus theory by sigma whole square. But if your errors are correlated, then you must have a covariance matrix. That is now data minus theory transpose times inverse covariance times data minus theory. I am defined chi-square here. The simple chi-square and the covmat chi-square is also there. Let's not go into the details there. Tau. So tau data, I have a single point Planck from the Planck observation. We have constrained for a baseline model. I'm using the one part of the baseline model where I'm assuming the tan hyperbolic model, but I am allowing the width to be freely vary. Okay, I'm allowing the width to freely vary. So there, okay, but I am using the constraint of tau data. In general, in practice, you should not do that. Okay, you have to vary that model with the Planck power spectrum itself. But here I just wanted you to have a test of how the parameter estimation is being done. Tau data is this. Tau chi-square, I am just plotting it here. Now remember, there are other data. For example, if now I am plotting the tau chi-square, let me just combine. Okay. Yep. If I vary the parameters and simply say that find the best fit, I find that the reionization redshift, where the reionization was halfway done, has the best fit of 7.8 redshift, and it has a width of 0.5. Now, neutral hydrogen or free electron fraction data. There are different data sets I have plotted here, from different observations. Okay, all the references are also provided here, and chi-square from this neutral hydrogen data you can compute here as well. You can compute QH to log like, QH to tau log like. That means that you are adding the chi-square from the optical depth and from the neutral hydrogen. Neutral hydrogen I need because CMB doesn't say when the reionization was finished. Did you have any discussion on the Gunn-Peterson optical depth? Neutral hydrogen around redshift 4 or something like that. Anybody? Okay, so what is the free electron? Okay, what is the neutral hydrogen fraction around redshift 4, 3 or 4? Order of magnitude. Good. That means our universe is ionized. Okay, so by redshift 4 or something like that, you will find that, for example, here around redshift 5 or something like that, your QH2 or the ionization fraction is nearly 0.996 or something like that with these errors. Okay, so we are using that. CMB doesn't tell you when the reionization was finished. Okay, so that is why you need at least 1 point. You don't have to use all the points. I'm using that, but you can also trace that without these points. Now what I'm doing is that I'm using Markov Chain Monte Carlo. In any of the courses, have you had any exposure on Markov Chain Monte Carlo? Have you used MC? Yes or no? Okay, not much. Can you tell shortly? Okay, no. Okay, good. Okay, fine. So if I discuss any part of dark energy, then I'm going to discuss that in detail. But let me just tell you that now the prior thing comes. Okay. Till now, in the CMB CAM, what we are doing is that we were giving parameters, values, fixed values for which I was getting one pause spectrum. Just assume that I have 6 parameters. Okay, or let's say I was changing AS, the amplitude. I was saying that the pause spectrum changes. So for 2 parameter changes, for 1 parameter, for 2 values, I was getting 2 CLs. Now I make 100 changes in that parameter AS. I will get 100 CLs. Now there is another parameter NS. That also can change 100 times, let's say. It can change infinite times, but let's say I'm saying that I have 100 grid points of square where NS is gridded in 100 points and AS is gridded in 100 points. I will get 100 cross 100 power spectrum. Means 100 means basically how much? 10,000 power spectrum. Now, all this 10,000 power spectrum will not feed the data to the same extent because of the chi-square, right? Theory minus data divided by sigma whole square. So theory minus data, if some power spectrum says that, okay, this amplitude is very high, it will be rejected. So you have 10,000. Now let's say I have 6 parameters. So it will be 100 to the 6 if the gridding is the same. You cannot simply test the chi-square and see what is the best, or also you cannot get the errors on those parameters in a finite amount of time, because it takes time to calculate these CLs and compare with the data. That is why you take a approach, okay, called Monte Carlo. Now it is called Markov chain if the chain is Markovian. It follows certain steps. It can have different types of sampling as well. So these are called different sampling. Okay, Metropolis testing method, nested samplings, etc. Let me start with a very simple thing. Let's say I have different. I have, let's say, if if I have n-dimensional parameter space, I start with single value of these n's. Okay, I start with a single value. I have n set of points. If I have two values, I have just two sets of points. For example, here I have just two dimension. What are the two dimension? One is redshift ZRE and one is this delta. Let's see. One is this ZRE and one is this delta. Okay. So what I was doing is that I was asking this minimize psi p minimize function to minimize this chi-square by varying this ZRE and delta ZRE using certain method called Nelder-Mead. Then I have added other chi-squares, and then what I'm asking is that I'm asking it this MC to perform a Markov chain Monte Carlo. What it says that is that you start with a point. Start with a point. Let's say these are the best fit points that I have found. I start with a point with a particular width around that point. I find a particular Gaussian ball around that point, around this point, in 2 dimension. Okay, so it is a particular Gaussian ball. In 2 dimension, it is just a circle. You take that point, you randomly generate different points within that small ball. Then you take a step, you take a jump, and see that first you calculate for that point where you started, what is the chi-square. Then you take a jump, see that whether your chi-square is lower or higher. If the chi-square is lower, that means it is better. You accept that point. If the chi-square is lower, you still accept that point with certain weight. The weight is given by the ratio of the likelihoods. Likelihood is basically e square, e to the minus chi-square by 2 for this discussion. So then you take the next step, then you take the next step. Then you need to discuss how many walkers are there. These are random walks. In these random walks, you accept or reject points. I have 100 random walkers. Okay. And I say that take 500 iterations. Cosmo IMSc also does that, but I cannot show you in this time frame. It takes about at least 6 hours to finish. So I take for each of these walks, each of the walkers, I take 100 iterations. Okay, and I try to minimize this tau log likelihood plus QH2. Let us start the run. See, it is taking different iterations. So it is 100 walkers are running and they are completing these iterations. 100 initial points are generated. Next point is generated depending on the ratio of the likelihoods. Then it goes to another step, another step, another step. It proceeds. I have been able to calculate till 87. It is going to take 2 minutes. In the 2 minutes, in between 2 minutes, please ask questions. Please ask questions. The reanimation optical on reanimation optical depth, please. Super simple. Everybody understood everything? Okay. After this lecture is finished, the workshop is finished, I'm going to also upload these notebooks in my GitLab. You can also go there. Anyway, you will anyway have this, so it's pointless if I say.
Sir, this likelihood we will get for all the parameters for CMB fitting, right? Or only for tau you are doing here?
No. Okay. So that this likelihood means that this is a okay. Tau is already constrained with CMB. I'm just trying to show you a Markov chain Monte Carlo process where I am using the tau that is already constrained by CMB with a mean value which is constrained to be 0.0561 with an error bar of 0.0071. Okay. Using this constraint, I am saying that I am now varying my reionization history by varying ZRE and delta. And I'm trying to find what is my constraint on ZRE and delta if tau lies between if the tau value is 0.0561 plus minus 0.0071 and some constraints on the neutral hydrogen data. Clear?
Okay, yeah.
Okay. Now I plot the random walks. Why it is not plotting? Should plot. Yeah. You see, it started with some point ZRE. Then it takes random walks. Each of the walkers are taking random walks, either accepted or rejected, either accepted or rejected. Delta also, it is taking random walks. So each point, basically, we are taking pair of points. So these pair of points are doing random walks. So these are different iterations. Okay, I'm just plotting up to 50 iterations. From there, you can see that our data says that your theory has to be in between these dense regions, because in these dense regions means that your points are accepted with higher confidence. These are accepted points and these regions. So you can get the posterior distribution saying that how dense the points are in this parameter space. Okay, it's called posterior mass function. You can basically get this distribution, and from there you can ask what is the correlation between parameters and what is the marginalized posteriors. So you can see I have been able to get the constraints after this Monte Carlo steps. I have been able to constrain ZRE and delta Z using my data. So this is the comparison of model with the data using Markov chain Monte Carlo. So I'm solving my model, getting the tau, getting the XC, and then, so there are two data sets. One is the tau. I'm integrating the free electron fraction. So I take a value of ZRE and delta. I get a line, that is the reionization history line, integrating, getting the tau, optical depth. Also, I'm integrating, I'm also finding that for this delta Z and tau, at what redshift, what are the neutral hydrogen fractions. Getting that, I'm comparing that data as well, getting this two chi-square, one from tau and one from neutral hydrogen, adding them and seeing what is the whether this value is matching with the data or not, depending on the chi-square. And from there, using the random walks, I can get the posterior density. You can see that I have been able to constrain it, and these are the correlations. Somebody was asking me what are the dependence, whether one parameter depends on another parameter. I said no, this is not a question of dependence, whether these parameters are correlated. As you can see, yes, these parameters are correlated. That means if ZRE increases, you have to also increase delta Z in order to fit the data. If ZRE decreases, you also have to decrease the delta Z. Otherwise, you will not be able to fit the tau. Okay. You see, then these are the best fit with the error bars. Okay, so these are, sorry, mean value with the error bars. So it says that my reionization rate, reionization redshift will be 7.19 plus 0.16 in 1 sigma and minus 0.12 in 2 sigma. So this 1 sigma and 2 sigma values, I hope you have understanding. Otherwise, I can discuss this if I discuss the dark energy.
So, sir, these three circles are sigmas. So one circle is 1 sigma.
Yes, inner circle is 1 sigma. So you see, these are the most dense points, black lines. Okay, then it becomes thinner and thinner. Okay, so these are the sigma. So from there, you can understand what is the most dense points, and then the outer side, what are the lesser dense points, but includes the 2 sigma like contours or 2 sigma like points, and etc. and then you draw the equal sigma hypersurfaces. Okay, equal sigma lines. That's what you get. Now we can simply plot the samples from these samples to sigma. From all the samples is collected, let's say I'm getting the center of the samples, and then I am plotting the samples that are matching with the data. So these are the samples of reionization history. So see, we have been able to constrain the history of reionization using the data, and these are the histories that are allowed by the data. So these are randomly selected points from this Markov chain Monte Carlo that are accepted. Okay. Assignments. Change the reionization history using Duspis-Akhanim model of reionization parameterization. It is there. I have given the reference. Remove the constraints QH2 before Z equal to 6.5. So I would like you to make your hands dirty with this and remove the constraint this after an obtain constraints and get the constraints. Okay, and get back to me. Okay, this finishes. Now I think I need to stop within 5 minutes. In that case, what I'm going to do is that I'm going to ask you to follow these instructions. Planck likelihood installation. Do install Planck likelihood at your own time. We are not going to run this. Then Planck grid analysis. You do the Planck grid analysis. You basically download this and the full thing. And Planck data also you can download. And then, okay, then you just these are the Planck grids are basically what Planck has already run and given you the grid. Their run results are publicly available. You just do the post process. The post process is done with getdist, and there is a getdist post process file that I have already shared with you. Getdist post process.ipynb. If not, then let me just share it with you here. Sensation Planck grid. Get it post process.ipynb. I'm sharing it with your in the node in the chat box. Now Firefox. So similarly, when you do this Planck analysis, you have lots of points you have lots of parameters. Okay, so the first 6 parameters I'm analyzing here are basically the parameters that I have run with or Planck has run with. So you will download the Planck grids, and then what I'm doing is that I'm just comparing 2 Planck analysis. One when this TTTEE and low L and low E. For this, look at my lecture yesterday. Planck likelihood are used, lensing is used, and then another is basically when you are using all this data plus BAO plus Pantheon 18 dataset. Okay, BAO dataset you are using and also supernova dataset you are using. And then what you are asking is that run it and get me the estimated parameters. So for some reason it is not showing here, but I have another one open for you here. When you do that, just like what we discussed here, also you will get constraints for all these parameters: omega baryon square, omega CDM square, omega 100 theta MC, tau, AS, NS, and these are derived parameters. Okay, so from theta MC and other parameters you can derive H0. Sigma 8, I already discussed sigma 8 yesterday. This is another derived parameter integration of the primordial matter power spectrum and the window function omega matter, total omega and omega lambda. Okay, and as you can see, so we have different types of constraints. If you have less data, TTTE, low L, low E, lensing, just Planck data, the red are the constraints. But if you add other data sets like BAO and Pantheon, they also constrain more. So they constrain other, for example, Pantheon dataset will constrain the omega matter a little bit in a not better, but in a different direction. So there will be intersection between the contours, and you can see that the red ones, the blue contours, are more constraining than the red contours. Okay, so as you can see that blue is able to, so if you add more data, you are able to get better constraints. Okay, unless there are tensions between the data sets. Okay, now you can simply ask get this to get the samples. I'm just leaving it for you to just have a look and get parameter values and 95%. Remember, these are 95% limits. In my last notebook, I was using 68% limits for the parameter constraints. I was just showing that, but these are 95%. So it says that your omega baryonic square value is 0.02237 plus of 0.00029. So you can see that how accurately they are constrained. For example, if it is 95%, then the 68% will be 0.00014 or something like that. So we have been able to do it very well. So H0, we discussed that there is a H0 problem in Planck, right? So let's go down and see what is the value of H0 from Planck alone. 67.4 plus minus 1. So that means at 68%, it is 68.7.4 plus minus 0.5. Have a look at my lecture yesterday. Here, the tension between Planck and other data sets. Yeah, 67.4 plus minus 0.5. And what are you getting here? Sorry, here 67.4 plus minus 0.5 if it is 68%. Okay, this is 2 sigma, so 1 sigma is 0.5. So now you can see that the part that I skipped here is just the run, but I have given you all the information how to do the run, how to install the Planck likelihood, etc. Once you do the run, then you can simply do this get dist analysis, and then you will be able to find the constraints. So this is the full hands-on session. This was the full hands-on session from how to generate a theory, get the understand the theory, what are the theoretical implications of CMB, get the Monte Carlo, a simple step of Monte Carlo that we can do in 10 minutes or something like that, and then get the Planck grid and do the post-processing and get the constraints on the parameters of your model. Okay, get the posteriors and also constraints on the parameter of the model. So I hope you are able to understand that. So with that, let me just conclude this session. There were a few other things that I wanted to discuss, but anyway, you will be able to get a hold of this if you just follow the assignments or to-do list. Okay, that I have supplied you already. Okay, let me stop here and take questions. If you have any time to take questions, or I can simply just sign off. Let me stop share. Okay.
Sir?
Maybe we can take a couple of questions. Okay.
Sure.
Yeah. Sir, so it is said that there is like around 5 sigma tension between the both measurements of local measurements and the this CMB measurements for the H0. So this 5 sigma. So what is that 5 sigma? Can you explain from here? Like, so it is, yeah.
Yeah. So let's say I am, let's say I am, for a very simple understanding, I am calculating the value of a parameter A. And let's say my experiment 1, but using 2 experiments. Experiment 1 is extremely precise. Okay. Let's say it gets the value equal to, let's say 10, parameter A value is 10 plus minus 0.1 or something like that, so that it is very small. And I do another observation where I get the value of A, another experiment where I get the value of A to be 0. Okay, and the error bar is plus minus 2. Okay, I get the value 0, but the error bar is plus minus 2 in 1 sigma. So you see, in order to match it with the observation A, you need 5 sigmas, 5 into 2, 5 sigmas to reach 10. So that is called that we are in 5 sigma tension. So the mean value of observation A is 5 sigma apart from the observation B. Sorry, mean value of parameter A from observation A. Sorry, their experiments are 1 and 2, and the parameter value is A. Parameter name is A. So the mean value of parameter A in observation 1 is 5 sigma away from the mean value of parameter A in observation 2. Clear?
So yeah, so basically the experiment which is precise, we are not taking into account. We are accounting for the experiment which is not very precise.
You can
So
also do that. You
we
can take the square root of sigma 1 square plus sigma 2 square. But I just wanted to give you a simple description.
Okay. So yeah, so
Inverse square
5
error.
sigma is yeah.
Yeah, tell me.
So yeah, I got that. Thank you.
Okay, so if there are no more questions, I mean, you can ask me the questions on in that Slack channel or after during this, and what changes to make in CAM to get the CMB power spectrum if one has inflation model or for a choice of potential. Oh, for that you need to combine bingo with CAM. Okay, so in place of this T initial power spectrum, you need to call bingo from there. In my code bingo, you can simply call bingo, or if you have a potential that is simply giving you the power spectrum, and you have the analytical spectrum, you don't have to use bingo. You simply write the form of the power spectrum that is dependent on the potential, and you define the potential parameters, and then that's how. And you instead of AS and NS, you will get the constraints on your potential parameters. Let's say if your potential is m square phi square, you will get constraints on m. What Planck has measured is the optical depth due to. Yes, optical depth to reionization. Yes, that is the free parameter. You see my lecture here. These are the parameters for the baseline model Planck has run with. These are the parameters, the yellow ones. Omega Variance square, omega CDM square, 100 theta MC tau, NS and AS. So tau is Thomson scattering optical depth due to reionization. Okay, as you can see here. Okay. Okay then. Thank you. I think that concludes the session. Supradik, over to you.
Okay, so end of a very exciting session. So on behalf of the TIH as well as on behalf of the participants, let us thank Dhiraj once again for a very wonderful series of lectures and exciting hands-on sessions on early universe and dark energy. I'm pretty sure the participants will benefit a lot from that. Okay, so there is a chance, as he has already announced, there is a chance that we may have him here once again discussing dark energy. But till then, let us give him a big hand. Thank you once again, Dhiraj, for everything.
Okay.
Okay, so see you all maybe at 2:20 once again with Dit.
Have a great
Thank
time.
you.
Bye.